So people wear like this, then tighten. Yeah.
Main goal is to look at how do I build such a system, how it's scalable, so it's really like I will say that. Yeah, I should. Oh, next. Ah, okay, yeah, I will. Then now I will. Should catch up. A lot of other postdocs looking for positions, but they want to do experiments. Yeah, and afford it. That would be really big for like remember this right now. Yeah, at first, like a little bit short period of time getting good people I wasn't the ships. Not like a
Transfer your presentation. Yeah, I did. Sorry. I don't I was with Professor. Oh, sure, yeah. So then he was there for about 2 years and then yeah, I remember. Yeah, I was. So I could meet my friends from Africa. So I said, but now knowing that you are going, maybe I didn't. Yeah, just experiments. Oh, it seems. If I don't do manual, it's fine. It kind of looks kind of up. I mean, oh, it's not. It's there. Seems like it takes a while. It takes a while. Or should I just use my hands in that case, I can give you another. The battery. Because now it's vibrating a lot. I think there are too many receivers in the CPU. Too many receivers in the CPU. I think maybe I'll just use the keyboard. How about that? This is the keyboard, right? Maybe I just put the keyboard here and then I just use my hands. It's easier. No? Receiver only one, right? Only one. Yeah. I mean, there are two thumb drives. I don't know. One is yours, one is yeah. So the delay is like one receiver, so it's fine. Right? Yeah. Yeah, okay, welcome back. My name is Durgesh. So this session, I'll be chairing this session. So this session has two keynote talks. Each will be of 30 minutes. which is 27 minutes of talk and 3 minutes of question answers after the talk. So the first speaker is Professor Kelvin Fong from NUS, and he'll be talking about domain-specific spintronic systems through system technology co-design. So let's welcome Prof. Kelvin.
All right, good morning, everybody. Thank you for organizing this nice symposium and inviting me to give a presentation on my research. And thank you for the wonderful introduction. So today I'll talk a lot about domain-specific spintronic systems and focus a lot more on system technology co-design. So I looked at the schedule of the talks in the symposium, so most people are focused on very specific topics. My research actually straddles a lot of different areas. So I go from devices actually all the way up to algorithms. And that's the concept of system technology co-design. So why is there a need to look at research in such a different fashion? So down here, I present a few different data. So on the left, you can see that there's this graph that's been sketched by the economist. Basically, what they show over here is that over the years, how much compute power is being generated by computing systems. And if you look at the modern era section, right, somewhere at around 2010, there's a big jump in terms of the compute power that we actually use. So where did that come about? If you look at the applications, these are very specific applications, right? These are specifically to deal with machine learning. So if you look at the machine learning applications, the amount of compute they demand actually increases much, much faster than what compute was before. And this actually introduces a problem because from a technology point of view, energy efficiency has not been catching up. So if you look at the graph on the right, so MIT Technology Review actually looked at the equivalent carbon emissions coming from compute. So you can see that this transformer network, which is one of the most popular networks for natural language processing that's used by your Google's, Baidu as well. You see, it consumes orders of magnitude more carbon because of energy consumption. So what this means is that if you look at from a compute perspective, we need to do something to improve energy efficiency, right? And one of the data that has been shown by Bill Daly from NVIDIA is to look at memory consumption. So if you look at what NVIDIA did, they actually showed data in terms of how much energy is consumed by different types of memory accesses, right? If you are just performing a simple 64-bit multiplication, you use roughly about 1 picojoules of energy. But if you are going off chip to DRAM to access data for your machine learning, you consume 16 nanojoules. So that is 16,000 times more energy than just doing a simple compute. So what this means is that from an energy efficiency perspective, you would like to actually keep your data as close as possible to the processor. You don't want to go off chip to access the memory, right? So if you look at the state of the art in terms of where we are at with all these computing, right? People have done very, very interesting work. We have used analog crossbars, for example, shown in the bottom left over here, to do analog matrix vector modifications. And even companies like Intel, for example, have been making very, very interesting architectures to accelerate some machine learning algorithms. And in fact, I think the state of the art is this Leaky 2. So that actually computes spiking neural networks. So if you don't know what those are, I'll actually talk a little bit about those later on. So the key point or the key message is that if you look at the research perspective, so everyone's working in their own domains, but there's a big opportunity to develop systems and microarchitectures that utilizes circuit design techniques as well as algorithm aspects of your applications to achieve and improve energy efficiency for compute. Now, in fact, when I started out in this career over here in NUS, what is interesting is that there is an additional degree of freedom that not too many people are looking at, and that has to do with things like materials and things like packaging. So if you look at materials-wise, there are a lot of different options available. You have a lot of spintronics and topological materials, for example, that can be used to make interesting devices, and I'll talk about some of those later on. There are other folks in the community that have looked at multiferroics, and then, the previous speaker looked at 2D materials. An emerging area is to look at Skyrmionics, and in line with the 2D material side, people have been looking at things like valuetronics, for example. So you could use these interesting materials and physics to think of, what are the new kinds of devices that you can have and target those for very specific applications of algorithms. So that's the idea. Now, on the other side, you can also think of packaging. At a higher level, people make all these different kinds of chips. You could integrate them together in different kinds of fanciful packaging, and that could also target different kinds of applications. So that's a more futuristic view. For example, you can think of your, automated autonomous vehicles. You might have electronics even embedded on the windshield itself. They could do some compute over there, and then that feeds into how the car operates, right? But that, I think, is something that's a long way to go. But again, all these different techniques can come in together to enable these kinds of applications. So I understand that a lot of people here might not understand what this idea of system technology co-design is about. So I just, briefly talk about that so that you can understand why I talk about things in terms of algorithms working with circuits and devices. So in the traditional model of how research is done, typically people look at different levels. You look at devices and you focus purely on devices. You look at circuits, you focus purely on circuits. You look at systems, you focus purely on systems. And what happens is, from a development point of view, what you do is, okay, you have a certain design, you want to use MOSFETs. So you take the MOSFET model, you build your circuits. After you build your circuits, you analyze at the system level how it performs. But there's always a feedback path, right? So in the feedback, what happens is, let's say, I was in AMD before. The way it works is that you look at your system level design, you say that, all right, I want to hit certain targets, but I need to improve my MOSFET in a certain way. Maybe for energy efficiency, for power, or for performance. So then you have to iterate back and go from the system level and feed the information back down to the device engineers to tell them, okay, what are the things you want to improve, right? And where are the opportunities, for example. But in system technology co-design, you actually straddle everything, right? You're not working individually at every level. So the kinds of things that I work on in my group, we look at devices, we look at, okay, if I want to make, for example, a neuron, right? And I'll talk about what a neuron is later on. What kind of devices or device structures I should have? Because I need certain kinds of behavior, right? I need certain kinds of transfer characteristic. Once I have that, okay, I build the circuits. And I look at, all right, at a system level point of view, how am I going to organize the devices together into my array? How am I going to map the algorithms down to that architecture so that it actually performs the function that I want, right? So there's a need to actually go through this a very vertical kind of research in order to look at these kind of systems. So now, having talked about the main motivation and how we approach things, I'll just quickly cover the outline of my talk today. So I'll talk about three key things. So the first thing I'll talk about are basically computing models, right? And then we look at, from the computing models, I'll focus specifically on one, which is the spiking neural networks. I'll talk about why we look at that later on. And basically, we look at why spintronics, right? What kind of spintronic devices that we can have. And then I'll conclude the talk for today. So let's look at the computing models and approaches, right? Now, one of the key things about machine learning, if you look at why machine learning is so popular, is that you can actually build the algorithm, train it, and it performs, very, very fantastic on a wide range of cognitive tasks. Natural language processing. If you think about back before machine learning, natural language processing was actually a very, very difficult area to work in, right? But because of machine learning, you can actually do all this training and fanciful stuff, and things actually perform very well. So what's the basic idea of machine learning? Well, the idea is you look at the biological neural network, you take inspiration from it, and you look at how the algorithm behaves. So there's a lot of neuroscience involved. And what people say is that, okay, if you look at a component of a biological neural network, it just consists of a neuron, right? Biological neuron. And if you look at a neuron, you can actually abstract out certain kinds of computation out of it. So what people have found out is that, okay, if I look at the entire mathematical operation, it looks something like this over here. So you have an axon, which is basically the signal transmission mode for your neurons. That's how the neurons communicate. You send spikes or signals down the axons. And there's actually a synapse, a synaptic connection between the axon and the receiving neuron. So the purpose of these synapses are to actually modulate the input signal. So there's a weight that gets involved. And the receiving neuron looks at all the input signals, it looks at all the modulated signals, it sums it up and compares to some threshold. If it's above a threshold, then it fires a spike to the next neuron. If it's below a threshold, then it doesn't fire a spike. It just rests. So what kinds of thresholding functions there are? Well, it's not quite a step function, like what I show over here. Well, in some sense, if you look at actual biological neural networks, it's a little bit like a step function. But the most powerful neural networks that people have looked at today, they use other kinds of functions, like for example, sigmoid functions. They might have looked at hyperbolic tangent functions, even linear functions, for example. Rectified linear is one of the more popular ones. But if you look at how we were to build such a system, it's actually very difficult to use CMOS alone to build these systems. So in my research, actually, we've seen that a lot of things can be done with very interesting spintronic devices. So for example, you can use things like current transmission to actually send signals between neurons. You can use crossbar arrays to do vector matrix multiplication, and this is one thing I'll cover later on. In fact, I think earlier this year, Samsung got a Nature paper just to demonstrate that this works at scale, right? And you can use actually very interesting spintronic devices to do analog dot products. So one such device is over here. You can use something like a non-local spin injection, for example, to do thresholding. And if you look at your threshold function, you can make very, very fanciful devices. And you can implement many, many different kinds of activation functions. So you could do step function, you could do linear functions, you can even do sigmoid functions. And the basic idea is just you use spin current to switch the device. And depending on how you make the switching happen, you could possibly get different kinds of activation functions. Now, if you look at the neural networks, right, why is it that a lot of people today are looking at in-memory computing? And the reason is because if you go down to the operations of your neural networks, they're nothing more than just matrix multiplications, right? So if you look at, for example, over here, I'm showing you one of the early neural networks, or this is specifically a convolutional neural network. So it's been designed to actually do handwritten digit recognition. So as input, you give, for example, a number, or in this case, a letter A is given as an input. It would go through the network does some convolution operations and thresholding, and at the output, it tells you, okay, is this a letter A, is this a letter B, or whatever, right? You have to train to do something. So if you look at such an approach, yes, you're doing all these operations, but there are a lot of inefficiencies. So where are the inefficiencies coming from? Now, if you look at the computation in every layer, you have to wait for the output of the previous layer to be ready in order for that layer to compute. So there's some waiting time needed. And in fact, if you look at these kinds of neural networks, there are a lot of redundant operations, right? If you have any zeros in your weights or your inputs, the system would still have to compute, even though it's a zero, right? The result is a simple zero. And it has to wait for that zero in order to do the next computation. So there are a whole bunch of different inefficiencies, and actually that is bad from an energy consumption point of view. Now, if you look at the past about 10 years or so, people have been very interested in a different kind of approach to neural networks. So that is this spiking neural network that I've shown here. So what is interesting about the spiking neural networks is that it actually uses a lot of concepts from neuroscience to build the same kind of neural network. Instead of using the numbers as in the previous slide, right, for conventional neural networks, spiking neural networks compute and convey information in terms of spikes, individual spikes. It's pretty much like how your biological neuron works. So every time you send a spike from one neuron to another, if there's a spike, then some computation happens. If there's no spike, the neuron does nothing, right? Or it could leak, for example. So the nice thing about such an approach from an algorithm point of view is that everything is fully parallel in both the spatial and temporal dimension. Now, if you think about the way the network behaves, if an input spike comes in at the input, the output doesn't have to wait for that spike to come in. It just looks at whatever spike it sees at its own input at that particular time, it can do a computation. So in spiking neural networks, you have this time dimension where information does take a bit of time to flow from the input to the output, but at every instant when you want to do the computation, everything is extremely parallel. You don't have to wait. Nothing has to wait, right? And you only compute when there's a spike. So as a result, you don't really have any redundant computation, right? So you can make use of this to actually make the entire system a lot more energy efficient, or it just consumes a lot lower power. Now, what's the behavior of the synapse and the neuron? So we need to think of how to make all these things in hardware, right? So let's look at, for example, the synapse and what it does. Okay? So from the algorithm point of view, the synaptic weight just determines the effect a spike has on a neuron. It has to modulate the effect, right? So if a spike comes in, this weight has to adjust, okay, is this going to be 1x? Is this going to be half, or is this going to be a quarter or lesser? What is the effect on the neuron itself? So that's the purpose of the synaptic weight. Now from hardware, what we need to do is actually convert the spike stimulus into a representation that the neuron can time integrate into an action potential. So what this means is that from a hardware design point of view, you need to first determine what is the state that you use to represent the action potential. Okay? So when spikes come into your neuron, it needs to first convert the spike information into that which the neuron can integrate. And then the neuron just accumulates that information over time. If it exceeds some threshold, then it fires a spike. So that's the idea. So depending on what is the representation of an action potential, you have to design your synapse accordingly, right, in terms of technology. What about the integration? Well, from the neuron point of view, you have to time integrate the incoming spikes. You potentially need to use a leak. So what is a leak? If you think about the neuron, yes, it accumulates a spike, but over time, the neuron actually tries to relax back into some rest state. So that relaxation, you can think of it as a leak in terms of the accumulation in the action potential. Now, after the action potential exceeds a threshold, now your neuron has to fire. But not just fire, it actually has to reset back into a rest state, right? So there's these two things that need to be there. You need to have the fire and reset. You potentially need this refractory period. Now in the biological network, for example, after your neuron fires a spike, it actually takes some rest time. And this is the refractory period. Within this time, it doesn't respond to any input spikes, right? So that's what the refractory does. So how do we build the hardware for a neuron? Well, first you need to be able to accumulate the effect of your incoming spike, and you need some way to compare with threshold. Okay, so this is very important. Now, after you do that, if the action potential exceeds the threshold, now as the fire, and you might need to do this relaxation step to replicate the refractory period. So if you look at the research that's been done, a lot of people have done these things in different ways. It could be circuit techniques, it could be device techniques. So the rest of my presentation, I'll talk a little bit about from the spintronic implementation point of view, what have people done. Now, before I talk about the neuromorphic stuff, this presentation here, I talk about domain specific. So domain specific means that we actually look at different types of very specific algorithms. Neuromorphic is one of them. In fact, one of the new kinds of things that people are very interested in is this thing called the Ising model. So it's actually a competition to the quantum model. Basically, what you do is you can encode a lot of optimization problems in terms of the Hamiltonian in your Ising model. And all you do is you make a circuit that has that kind of Hamiltonian in the energy landscape, and you run things like quantum annealing kind of algorithms, or in this case, we run simulated annealing. Another method that people use is this simulated bifurcation. You basically relax the system to the ground state, and the ground state is the solution to your optimization problem. But I'll not talk about this in today's presentation. This is actually a very broad work. If you go out and look at people looking at oscillators today, looking at spintronic probabilistic bits like p-bits from UCSB, for example. They talk about this kind of applications. But you can implement those with spintronics as well. Right? So today I'll just focus solely on spiking neural network hardware accelerators using spintronics. So if we want to build such a hardware, there's actually a general template. And the template that people use is this crossbar array that does the vector matrix multiplication in your machine learning algorithms. But the reason why we want to use a crossbar like this is because if you look at your neural networks, one of the most important aspect of it is you need connections. Right? The number of connections you have actually gives the power to the behavior neural network. So a crossbar is probably the most dense connectivity that you can achieve using the hardware that we know. So that's why we use crossbars. Now, once you have such a template, then implementing the neurons and the synapses is just a matter of how you want to communicate information. What are the kinds of things in the algorithm that you want to incorporate? You want to work on it in a digital domain or analog domain, and what are the kinds of things that you want? You want stochasticity, do you need reset and things like that. So depending on what devices that you want or what the functionalities that you want, you make sure the devices that you have in such a design has these kind of different behavior or characteristics. So in terms of the synapses, right, let's talk about synapses first. There are a whole bunch of different synapses that have been proposed. I think the one that has been most popular in the spintronic domain is the binary synapse based on either SOT MTJs or the conventional two-terminal MTJs. So down here, you are just using the synapses or device sort of as a one-bit memory. So your synapses become one-bit synapses. 0 means that you don't have a connection. 1 means that you actually have a connection between one neuron to the next neuron. Now, it turns out if you use these binary synapses, these are very good for very, very specific networks. These are binarized and quantized neural networks. Okay? So in binarized and quantized neural networks, you're not representing numbers as complete floating point numbers. You use possibly fixed point numbers and a very low precision. Right? I think the highest that I've seen is roughly about 8 bits precision. But in fact, if you look at a lot of the works, you can actually get away with 5 bits. Right? That's the precision there. Now, one of the challenges in these synaptic connections is that if you use a two-terminal device, you actually have a competing requirement for the read and the write. So your read actually requires you to design the devices in a certain way, but if you want to write, you need to make sure you can flip the bit, right? So typically, if you make it easy to flip the bit, when you read, you can actually disturb the state that you store. So you have this competing requirement for read and write. So in terms of building these binary synapses, it turns out one of the more optimistic directions to look at is to look at multi-terminal devices, and you want to decouple the read and the write in those kind of devices. Right? So then you can do all these binarized neural networks. Now this work on the right over here basically looks at these 1T, 1MTJ kind of arrays. This was actually the work done by Samsung. So you can make this into a neural network to do XOR operations. Now, because in the interest of time, I don't want to talk too much about those other things, but I'll focus on the other kinds of spintronic synapses. Now, it turns out analog synapses are more interesting. So you can use RM, for example. That's been done by a lot of people, two-terminal RM crossbars. But I think more interestingly, you can actually use domain wall devices to actually make these kind of analog synapses. And I think one of the talks in this session will talk about these kind of domain wall synapses. Now, the idea over here is you're going to use voltage pulses, convert them into current pulses, and that will move the domain wall left and right in the device. Depending on the position of the domain wall, you get different sampling rates. Now, the same idea could be used if you use skyrmions. So instead of using domain wall position, the idea is you use either number of skyrmions, or you can use skyrmion position. So down here, I just showed 2 different works. One of the work that my group is publishing, it's currently under review, is to use a synapse that's based on skyrmion, and this is a quantized synapse. Nice thing about these kind of synapses is that you can get very good linearity in terms of the conductance modulation. And that's actually what you want from a spiking neural network perspective. Now, the basic idea for neurons, right? We just talk about synapses, but now we talk about neurons. So in neurons, you get something similar. Now, the big difference between the synapse and the neuron is that you need to build this thresholding function in the device. So one of the ways you can build a thresholding function is you look at the resistance in your domain wall synapse, and you just compare it with a reference MTJ, a reference resistance. And depending on this comparison, you can generate an output. Down here, I show two different ways of generating an output. It could be a current spike at the output, or it could be a voltage spike at the output. But the idea is the same, right? You're just converting the current into the domain wall position. Depending on position of domain wall, you kind of threshold and spike accordingly. Now, what about leak? I think today leak is the one that is a bit more tricky to implement. So one of the ways that you could implement the leak is to actually change the energy profile or the anisotropy profile in the device. So down here in this work, they propose 3 different ways of changing the energy profile to achieve the leak in a domain wall device. So one way is to change the shape of your domain wall strip. So down here is the side view on the left. Top here is the top-down view. So depending on the width of your nanowire, you get different anisotropy. So therefore, due to this gradient in anisotropy, the domain wall, after you keep it at one side, it starts to migrate back to the other side. It will go to some rest position. So that behaves like a leak. Another way that they show you could do it is you kind of do dipolar coupling between one magnetic layer on the bottom and your domain wall wire. So that's on the bottom here. So that coupling magnetic field would force the domain wall to go towards one side of the device. So that could also implement leak. And then of course, Prem here did some work on this domain wall devices as well. So you could just create this anisotropy gradient somehow, right? And then you could get the leak to happen. And in this case, if you look at the proposed device idea is that, okay, my domain wall starts here on the left. Whenever I have a spike, I would push a domain wall to the right. If it crosses the pin layer, that's where my MTJ is. I can detect it through the MTJ, so then it would fire a spike. But in the absence of any spike, the domain wall would just naturally move back to the left. But one of the problems, again, in such a device, and we are looking at it, is that after the neuron spikes, we need to somehow reset the neuron manually. So there are different options, and I think right now the most promising way is to actually inject a reverse current to move the domain wall back to the reset position. But the actual device structure, I think we still need to think how to actually make that work properly with process variations and stuff. Okay. Now there are other kinds of neurons. One way is to make a stochastic neuron. Just now we looked more at a deterministic neuron. So in stochastic neurons, the ideas are very straightforward. You just make use of thermal fluctuations or the right error rates in your MTJ or SOT device, and you use that as a mechanism for your compute. So that's the idea of this stochastic neuron. And what people have found is that if you actually just try to model your right error rates, it's a sigmoidal kind of function. So then you can use that as a way of doing your activation. Right? So down here, there's another structure. You could actually use a coupling between a magnetic layer over here to a ferromagnet layer that's on the top. And because of the grains of this ferromagnet, you actually get kind of stochastic switching. So you can actually use that also as a way of getting this stochasticity in the device. And then you can use that to make different neural networks and stuff like that. So I think one of the work that we have done with Professor Hyung-Soon Young, looking at that device, was that, okay, I can actually build different kinds of stochastic neural networks or even restricted boson machines. You can do handwritten digit recognition as well. But if you were to look at for the kinds of accuracy we're getting, actually energy efficiency is not that good. Energy consumption is still fairly high. I think for the MLP, the spiking kind of network, we're getting 50 nanojoules. So that is actually quite a lot higher than what we would like. So there are ways that we try to figure out how to reduce that. Now, coming back to the deterministic neurons, again, there are equivalents for using Skyrmionic devices. So just now we looked at the domain wall kind of devices. In fact, you could use that, use Skyrmionic devices to do the same thing. So what's the idea in the Skyrmionics? Well, you might want to use skyrmions because due to topological protection, it might be robust against different kinds of variations in temperature. Right? But of course, the biggest challenge to address in designing these skyrmionic devices is that you have the skyrmion Hall effect. So it limits the amount of current that you can drive the skyrmion in the device. The velocity becomes limited. Right? So one of the ways that you could possibly do that is to use a multi-layered device, like what I've shown here. So down here we have two ferromagnetic layers, and they need to be anti-ferromagnetically coupled. So this anti-ferromagnetic coupling actually helps keep the skyrmions together. And because the skyrmions in the two layers are pointing in opposite directions, when they move along the same direction, the Magnus force acting on them are actually acting in opposite directions. So the coupling itself, the anti-ferromagnetic coupling itself, tries to keep the two skyrmions together, and therefore it kind of mitigates the effect of the Magnus force. So then you could get these skyrmions to move in very, very straight and linear directions. And that helps you overcome certain problems. So at the hardware level, what we did was we took the Neuron, we architected it into the hardware array. So down here is actually the array of the devices. You have the Synaptic crossbar array up here. You have a Neurons array down here. And then you can actually train the network to do handwritten digit recognition again. Right? But down here, instead of using the machine learning algorithm, deep learning algorithm, we're using a spiking neural network algorithm. So it's a complete spiking algorithm. Basically, we take a deep learning algorithm, we convert to a spiking neural network equivalent, and run the algorithm over here. And what you can see is that from an energy consumption point of view, it's a lot more energy efficient. Right? You can actually get very, very good accuracies. I think down here we're showing 96% handwritten digit accuracy. Every neuron consumes on average about 1 femtojoule per time step. One time step is 2 nanoseconds. Right? So 1 femtojoule per 2 nanoseconds on average. And the scalability of this is actually pretty good. So if you want much, much lower energy consumption, you can just use fewer time steps to do the computation. In fact, what we show is that if you take about 1/5 the amount of time steps to run your computation, your accuracy does not degrade too much. You go from 96%, but it degrades to maybe only 93%. But because of the fewer time steps that you need, the amount of energy that you spend for each image classification is actually about 80% lower than what it was before. Okay? So you get that very, very good scalability. Okay, so now I just come to the conclusion of my talk, right? So I'm going to take a little unconventional method to doing a conclusion. So what I've done today is I've talked about the spiking neural network, for example, as an algorithm. And hopefully what I got across today is that if you were to look at how to build hardware that emulate these spiking neural networks, you can't just look at devices alone. You have to understand a little bit about the devices. You have to know how to put these devices in circuits, what are the algorithms, and how you're going to map the algorithms down onto the hardware. So therefore, this concept of co-design across the different levels of design abstraction becomes very important when you look at this research. Now, one of the other key takeaway points is that from an algorithm point of view, we really want to use these event-based approaches. And event-based approach is good because you can potentially get very good energy consumption and still hit the kind of accuracies that machine learning techniques are giving you. You don't really get a significant degradation. So it's really up to the applications folks to see, right, is this level of errors good enough for the application? How can I use different neural networks, put them together for the kinds of tasks that I need to perform? Now, there are some opportunities for research in this area, right? So the kinds of things that my group we are looking at right now is, okay, how do I actually reduce the energy they need to reset the neurons? Because if you really think about it, those should come naturally in your biological system. You don't want to consume additional energy just to reset the neuron. Another problem that, in fact, not just in neural networks, but even in these Ising machines that we found out is that it's really difficult for you to get very high fan-out in this kind of devices. Fan-out is actually a big problem. So if you look at, for example, the work in P-bit, right? A lot of what they have done is to actually sparsify the network. So sparsity helps in terms of reducing the fan-out, And as a result, you can actually get much better operation. Okay. Another area is how do you actually scale up these spiking neural network microarchitectures? I think that is not something that a lot of people have looked at. People have demonstrated very small networks and built those algorithms and then benchmark against what other people have done. All right, and then I'll just leave this over here, looking at Ising models. So that's actually another area that people are interested in from a domain-specific compute perspective. Okay. So that's all I have, and just quickly acknowledge the people as well as the collaborators and the grantors that have worked on the different projects in my group. All right, and thank you very much. I'm happy to take any questions.
I think we have already stated the time.
Yeah.
If you have questions to Professor Kelvin,